smartphone's run out of battery. I don't have a charger. What shall I do? Is that a solar panel? With solar power, I can charge up my smartphone. But how do I connect it to the smartphone? This should work. Let me try. No!
Solar energy generation refers to the conversion of solar energy into electrical energy. But what form of energy is coming from the sun? To understand the principle of solar energy generation, we have to understand electromagnetic waves.
Tissue, is that my solar panel? What are you doing with it?
My smartphone is out of battery. I was trying to charge it with the solar panel, but it doesn't work.
Solar panels are not used in this way. To know how solar panels work, we need to begin our discussion with sunlight.
The sun is bright and hot. What's special about it?
The sunlight that we see is visible light. It is visible to our bare eyes. But apart from visible light, the sun also emits other radiations, such as infrared and ultraviolet. All such visible light, infrared and ultraviolet are called EM waves.
EM waves? What are EM waves?
EM waves are a kind of wave, just like this spring. But EM waves can be transmitted without a medium. They travel in a vacuum at the speed of light, which is 300,000 kilometers per second. Classifying EM waves by their wavelengths, we can obtain a spectrum of EM waves.
Does the sun emit different kinds of EM waves?
The sun emits all kinds of EM waves. Because of the blockage by the Earth's atmosphere, the solar radiation that can reach the ground consists only of visible light and parts of ultraviolet and infrared radiations.
Oh, I see.
You look confused. Let me show you some experiments.
Can it be charged? Wait for me. Dr. Tong, infrared and ultraviolet radiations cannot be seen with bare eyes. What are their properties?
Try to put your hand here.
It is warm.
Yes, this is an infrared lamp. The light that you see with your eyes is red light, but not infrared radiation. Infrared radiation is invisible to human eyes. All hot objects emit infrared radiation, including our bodies. After absorbing infrared radiation, we will feel hot. So when you're near a fire or in front of an infrared lamp, you will feel hot.
And ultraviolet radiation?
This is an ultraviolet lamp. Ultraviolet radiation is harmful to our eyes. We have to wear goggles to ensure safety. Similarly, the violet light is not ultraviolet radiation. It is invisible to our eyes, but it does exist. The ozone layer in the atmosphere blocks most of the ultraviolet radiation. Only a small part can reach the ground. According to wavelengths, the ultraviolet radiation in sunlight can be classified into UVA, UVB, and UVC. The wavelength of UVA is the longest, while that of UVC is the shortest. The ultraviolet radiation reaching the ground is mostly UVA. All UVC is blocked by the atmosphere.
But how much energy is carried by visible light, infrared and ultraviolet radiations?
The energy of EM radiation is related to its wavelength. Shorter wavelengths mean higher energy. Among the three radiations mentioned, ultraviolet has the shortest wavelength. Its energy is the highest. Though UVC cannot reach the ground, it is able to kill germs because of its very high energy. Sometimes we use weak UVC lamps to sterilize.
Oh! How can we detect the radiations that are invisible to human eyes?
That's a good question. I have some experiments which can show you the composition of white light and how to detect infrared and ultraviolet radiations which are invisible to us. These are all LEDs. The wavelength here is 640 nanometers, which is red light. The wavelength decreases down the column. The wavelength of violet light is only 400 nanometers. Therefore, the range of visible light is between around 600 and 400 nanometers. White light consists of light of all colors. Look at the LEDs through the grating. What do you see?
I see a rainbow.
Right. The grating can separate white light into different colors. Red LEDs only emit red light. Therefore, only the red color is seen in the spectrum. However, white light consists of different colors. All the colors are here. Therefore, you can see a complete rainbow.
I see. How about infrared radiation? Ah, I know. It's like the actors in the action movies. They need to move carefully and pass through the infrared beams, otherwise the alarm will be triggered.
Hey, that's fictional. Take a look at this.
What is it? Oh, Dr. Tong, you look so cute, but why?
This is an infrared thermography camera. It can turn the invisible infrared radiation into a visible image. The white and red parts on the screen show the parts emitting the most infrared radiation. Those are the hottest parts. The blue parts indicate the parts emitting the least infrared radiation. They're the coolest parts.
Is it similar to the infrared detector that we use to measure our body temperature?
You're right. Do you see that my glasses appear blue?
Yes, that's interesting.
It is because infrared radiation cannot pass through glass. Therefore, the infrared radiation emitted from my eyes is blocked by the glasses. That is why you cannot see it.
Light can pass through glass, but infrared can't.
All right, this is a traditional incandescent lamp. It emits a lot of heat. Another lamp appears blue. It is an LED lamp we commonly use. It emits light with semiconductors and produces less heat. For incandescent lamps, most of the energy turns into heat. It is not the case for LEDs, so we no longer use incandescent lamps nowadays. We use LEDs instead.
More eco-friendly.
Exactly. I have a piece of cardboard here. The light spot of a red laser is bright, but nothing special happens on the cardboard. If I use a blue laser instead, the cardboard glows. It is because human eyes are more sensitive to red light than blue light. Thus, the red light appears brighter. The way we can see the energy of violet light is through fluorescence. The energy of violet light is high enough to make the fluorescent particles glow. Therefore, we can see the energy that is invisible to our eyes. Fluorescence also appears in some minerals. We will use an ultraviolet lamp. Let's change goggles first. Do you see the shiny spots?
It's twinkling.
In fact, it is the violet light or ultraviolet radiation that produces the fluorescent spots.
It's beautiful. Can I take it home?
Sure.
Thank you. We've just learnt that white light is a combination of different colours. After refraction, the sunlight is divided into different colours. That's a rainbow. But how do we know which colour is more abundant and which colour is less abundant?
Good question. I just wanted to talk about the spectrum. A spectrum tells us the intensity of light of different colours or at different wavelengths. This is a portable spectrometer. It can measure the spectra of the sky and the sun. The spectrometer has been connected to a smartphone. Pointing this optical fiber towards the sky can collect sunlight. The spectrum of the sky is displayed. Look at the rainbow on the screen. Where do you find the peak? What is the color?
It's blue.
Yes, the sky we see now appears blue because molecules in the atmosphere scatter sunlight. The scattering of blue light is more significant. That is why the sky appears blue and blue light dominates here. Let me show you the spectrum of the sun. Since sunlight is too strong, the reading is saturated if I point the fiber toward the sun directly. Do you see a small hole on the tape? I put the tape on the fiber. This helps block most of the sunlight. In this way, I can measure the spectrum of the sun.
Why does the curve peak near the green colour?
Yes, the sun really emits green light the most. The surface temperature of the sun is 5,000 to 6,000 Kelvin. At this temperature, green light is the most prevalent among all the emitted colors. There exist other colors for sure, such as red, violet, and blue light, but their intensities are lower.
Now I know the properties of sunlight. How do I charge my phone?
Before charging, we have to know which type of solar panel is better. Here are 3 types of solar panels. They have similar sizes. This is a monocrystalline solar panel. The middle one is a polycrystalline solar panel, and the one you are holding is an amorphous silicon solar panel. We perform a fair test by putting them under the same sunlight. The angles are nearly the same. The one in my right hand rotates the fastest. It is a monocrystalline solar panel. The polycrystalline one rotates at a rate in between. And which one rotates the slowest?
The amorphous silicon one, which I'm holding.
We assess how fast the motors rotate by simple inspection. It is inaccurate. Let's go back to the laboratory and place the solar panels under different kinds of radiation to test their output powers.
Okay.
Here are the three types of solar panels. They are monocrystalline, polycrystalline, and amorphous silicon solar panels. Each is connected to the same circuit. Here is a small watt meter. It can measure the output power of a solar panel. The unit is milliwatt. Let's start with infrared radiation. Here is the infrared lamp. Let's test the amorphous silicon solar panel first. What is the reading?
Less than 0.1 milliwatts.
Let's try the polycrystalline one. To have a fair test, the intensity and distance of the lamp should be kept constant. What is the reading?
About 210 milliwatts.
Now the monocrystalline one.
Okay.
What's the reading?
It's over 250 milliwatts.
Yes, the monocrystalline one is more efficient than the polycrystalline one.
What about other light sources?
Let's try visible light. We will make measurements with the three solar panels in turn. The output power of the amorphous silicon one is about 160 milliwatts. It is about 240 milliwatts for the polycrystalline one and about 280 milliwatts for the monocrystalline one. The monocrystalline one has the highest efficiency. The second highest is the polycrystalline one. Their efficiencies are similar but way more efficient than the amorphous silicon solar panel. Therefore, many solar power facilities use monocrystalline ones for maximizing efficiency.
Let's try the ultraviolet lamp.
UV radiation's harmful to human eyes. Let's wear safety goggles.
Got it.
We make measurements with the three solar panels again. The reading is very low for the amorphous silicon one. It is less than 1 milliwatt. The reading for the polycrystalline one is less than 20 milliwatts. It is about 20 milliwatts for the monocrystalline solar panel. It is worth noting that the three light sources we have used, infrared, visible, and ultraviolet lamps, have different output powers. The light sources are not comparable. We can only compare the performance of the three solar panels under each radiation. The monocrystalline solar panels have the highest efficiency, but they are the most expensive. Monocrystalline solar panels are widely used in many facilities. The efficiency of amorphous silicon solar panels is lower, but they have some advantages. They are flexible, light, and easy to carry. They are used in some portable facilities. Monocrystalline and polycrystalline solar panels are rigid and heavy. Therefore, monocrystalline or polycrystalline solar panels are widely used in permanent facilities, such as an array of solar panels installed on the rooftop. We have to notice that even though we've tested different kinds of radiation, solar energy generation mainly relies on the visible light and infrared radiation in sunlight. Sunlight reaching the ground contains very little ultraviolet radiation. Thus, we don't rely on ultraviolet radiation.
Now we know that monocrystalline solar panels have higher performance. If we cast very intense light on them, such as sunlight, would it generate a lot of electricity?
Generally speaking, more light allows the generation of more energy. However, the energy generated by solar panels will not indefinitely increase with brightness. We have the spotlight shining on the monocrystalline solar panel. Here is the reading. The unit is milliwatts. It is the energy output per unit time. Here is a smartphone. It is used to measure the intensity of light shining on the solar panel. We will gradually increase the brightness of the spotlight. Under different illuminants, we will measure the output power of the solar panel. Let's start with this illuminance. The illuminance now is about 13,100 lux. What is the reading of power?
It's about 48 milliwatts.
Increase the brightness.
Make it brighter.
It's about 26,200 lux now.
It's about 164 milliwatts.
Make it brighter.
It increases a lot.
It is now 36,900 lux.
It's over 210 milliwatts.
Make it brighter. It is 70,900 lux.
Strangely enough, it doesn't increase much. It's about 245 milliwatts only.
Make it brighter. It is 115,000 lux now.
It's about 260 milliwatts. It just increases a little bit. It seems to be saturated.
Although the illuminance increases rapidly, the output power doesn't increase that much. That means the solar panel is saturated. Even if the illuminance is further increased, the output power doesn't increase much. Therefore, even if the brightness continuously increases, the solar panel cannot give out more energy indefinitely. What if we compare the solar panels on sunny days and cloudy days? The sunlight is weaker on cloudy days and stronger on sunny days. More electricity is generated on sunny days. When the illuminance reaches a certain level, even if the brightness is further increased, like the sunlight is getting even stronger, it may not boost the amount of energy generated.
I see. We've talked a lot about solar panels. When can I charge my smartphone? It ran out of power and turned off.
Solar panels cannot be directly connected to a smartphone for charging. The solar panels are usually connected to some electronic components, such as inverters, and then connected to the appliances. To charge up by solar power, I have a charger powered by solar energy. It is ready for use.
But it is night time already. How do I use it?
I'm smart. I've already charged it with a solar panel in advance. You can use it now.
Why didn't you give it to me earlier?
Although a small solar panel cannot help much, they can work collectively. Behind me is the array of solar panels installed on the rooftop of the headquarters of EMSD. The array consists of 2,300 components. Each component consists of 72 monocrystalline solar cells connected in series. The maximum output power of the system is 350 kilowatts. It serves about 3 to 4% of the total power consumption of the headquarters of EMSD. Solar energy is an important source of renewable energy. EMSD introduced the Solar Harvest Scheme to subsidize schools and welfare NGOs to install solar energy generation systems. EMSD also assists them in joining the Feed-in tariff scheme. Beneficiaries can save on electricity bills, as well as use more renewable energy to support decarbonization work.